Welcome. In this video, I am going to explain to you how does my numerical software application work. We have six method im- implemented on this code. Let's discuss it one by one. Starting off the graphical method. This part of the code will help us generate our x and y values in order for our line to plot on the graph, where this will help us visualize where the root is located. This will find the sign change where x changes from x positive to negative x. After that, uh, this part of the code or algorithm will, will find more accurate route in order for our graph to display its route. Moving on to the incremental method. In the incremental method, this part of the code is our main loop where it ta- where it takes small steps in order to get to the maximum uh, x value, where it check if f of x is close to 0. If not 0, then it checks for any sign changes. After it checks or if any sign changes, it refines the route using a smaller steps. After that, if if it meets uh, if it meets the given tolerance set, then the iteration will stop. Moving on to the bisection method. In the bisection method, this part will find the interval with the sign change, where again uh, it where x changes from positive to negative. If there's not if there's no changes in the interval, then there is no changes or there is no change sign in the given interval. If there is, then it enumerate the intervals a and b. Then by using this algorithm and the bisection or formula, it calculates the midpoint, then evaluate the function at the ends and the midpoint. After that, it calculates the error, then then check if the given tolerance is set in order for it to stop. Moving on to the next method, the regular falsi method. Here in the regular falsi, it has the same as uh, the bisection method where it finds the interval with the sign changes. Moving on, and then it uses this formula to calculate the regular falsi method. After that, it calculates its error and it checks if the given set tolerance is met. On to the next method, the Newton-Raphson method. In the Newton-Raphson method, you must give an initial guess in order for it to work, in order for it to locate the root. After that, this part of your root is this part of your code is the most important part because this is your f of x and f prime x. Then, then after that, it calculates the next approximation or your next initial guess. And it calculates our error and check if the given if the given root if the given equation or I no no if the given tolerance is met, then it will stop the code. Moving on to the second method. On the second method, here we have two guesses. The initial guess and the second guess. This is your fx0 and fx1. And by using this algorithm, you calculate the next approximation or your next root guess. Then it checks and then it calculates the error by using this formula or algorithm, and it checks if the given set tolerance has been met. And that's all in my uh, Python in the Python code method. Moving on to the uh, actual program itself, the UI. Here, the here in the function is where we can uh, prompt our equation or any formula you want. It is versatile and flexible. And here we can have our examples given, or you can do it what you want to see in the graph. Then in the method, we select if what method we wanna select. And here in our parameter, where the search range from -5 to +5, then then the tolerance give and the max iteration. And here is the step size on our incremental and initial guess for both Newton-Raphson, and second method. And this is the second method. Okay, let's test it. Using this equation, let's find the root using the method of incremental method. As you can see, this is our root. And if we go here in our table, you can see that our root our root is 0.5672, which is correct. And let's try the Newton-Raphson. In the Newton-Raphson, you must do the initial guess. Let's say 1. And then here, let's use the sample 3. Since our our line is close to 1, then it gets the root in the left side of the uh, curve line or curve graph. And I think that's all. Thank you for watching the video.